Hey folks, in this video we're going to explore determinants and their relationship to the geometrical notion of volume. I assume that you've seen a little bit of linear algebra before. In particular, I assume you're familiar with the concepts of vector space, including vector addition and scalar multiplication, dimension, and related concepts like linear dependence, linear independence, and basis, and finally the concept of a linear map. But don't worry if you're not an expert on these. You may have already seen determinants before in some form or other. If you didn't understand them or found them strange and mysterious, this video might be helpful to you. In this video, we'll see that determinants measure n-dimensional oriented volume, and we'll see what that means. We'll also discover a fundamental relationship between n-dimensional volume and n plus 1-dimensional volume, namely that in a certain sense, which we'll make precise, n-dimensional volume is just n plus 1-dimensional volume measured relative to a fixed vector. This simple geometric fact explains important properties of determinants. Finally, we'll see that the geometric properties of determinants completely determine their algebraic properties. In particular, seemingly complicated formulas for computing determinants follow easily from the geometric properties. It's worth studying determinants because they have many important applications in mathematics. For example, with systems of equations, like solving n linear equations in n unknowns, or finding common roots of polynomials, in determining whether vectors are linearly dependent or independent, in describing the behavior of linear transformations, in particular characterizing rank, invertibility, and eigenvalues, in geometry, for example describing orientation and volume and solving other geometric problems, and in analysis, for example with multivariable integration and differentiation. In this video, we're going to focus on understanding determinants themselves and their fundamental properties, rather than focusing on applications. Once you understand the fundamentals, the applications become fairly straightforward. Before diving into that, however, I'd like to briefly highlight some salient points from the history of determinants. If you're not interested in history, you can safely skip past this part. Determinants are as old as linear algebra, or older depending upon how you define linear algebra. Importantly, determinants were discovered algebraically in connection with systems of equations, not geometrically in connection with volume. Also, they were initially discovered in simple cases, not in full generality. Determinants were used in China as early as the 1st century to solve certain systems of linear equations. This is evidenced by determinantal methods described in the 9 chapters on the mathematical arts, one of the earliest transmitted mathematical texts from China. Over 1,000 years later, the mathematician Seki Takakazu, also known as Seki Kova, used determinants in Japan in 1683. Seki was highly secretive about his methods, sharing them only with his closest students. Right around the same time, Leibniz independently discovered determinants in Europe. However, he didn't publish his results. In 1693, he wrote about them in a letter to L'Hopital. I don't know it for a fact, but I strongly suspect that he and L'Hopital were also trading hair care tips in their letters. Further development occurred in Europe in the 1700s. There were important contributions from mathematicians like Cramer, of Cramer's rule, Vandermonde, Laplace, Lagrange, Gauss, and others. Cauchy and Jacobi both published important work on determinants in the 1800s. Cauchy presented a paper in 1812 in which he summarized and generalized what was then known about determinants, improved notation and proofs, and established new results. Jacobi also made notable contributions, including functional determinants, and the Jacobian is named after him. Many historians view the modern theory of determinants as beginning with Cauchy and Jacobi. Inspired by geometry, Hermann Grassmann developed in the mid-1800s a highly original and modern approach to linear algebra, and created what is today called exterior algebra, which provides a geometric approach to the determinant. This approach has connections to our approach in this video. Grassmann's work was way ahead of its time and therefore not fully appreciated until later, although it was known to some prominent mathematicians like Peano. In the late 1800s, Weierstrass developed, and Kronecker used, an axiomatic approach to determinants which is still popular today, and which we will also make contact with in this video. It's important to note that matrices were introduced in their modern form only in the 1850s, long after determinants, by Cayley, although the term matrix was coined by Sylvester. In this photo, Cayley can be seen willing them into existence with the sheer power of his mind. Modern abstract linear algebra, with the view that a matrix is just a representation of a linear map, which is the more fundamental object, was heavily influenced by Emmy Noether and Emil Artin in the 1920s. Artin also popularized the axiomatic approach to determinants. In this video, we'll look at determinants from a thoroughly modern geometrical point of view. Although it can be illuminating to learn certain subjects in the way they developed historically, in the case of determinants, it's best to use hindsight to our advantage. So let's get started. In the plane R2, let AXY be the ordinary area of the parallelogram determined by the vectors x and y, as seen here. Recall from geometry that the area is just base times height. We're not going to worry about finding a formula to calculate the area just yet. Instead, we ask, what properties does A have? More specifically, how does A behave with respect to the vector space operations of addition and scalar multiplication? First, we see that the area determined by the vectors x and x plus y is the same as the area determined by x and y. In this picture, the parallelogram determined by x and x plus y is overlaid on top of the parallelogram determined by x and y. It's obvious that the two parallelograms have the same area because they have the same base and height. In fact, the parallelogram determined by x and x plus y is just a horizontal shear of the parallelogram determined by x and y. Similarly, the area determined by x plus y and y is the same as the area determined by x and y. It's worth drawing the picture yourself to see this. Next, if alpha is a non-negative scalar, then the area determined by the vectors alpha times x and y is just alpha times the area determined by x and y. In this picture, the parallelogram determined by alpha x and y is overlaid on top of the parallelogram determined by x and y. It's obvious that the area is scaled by alpha because the base is scaled by alpha while the height remains unchanged. Similarly, the area determined by x and alpha times y is just alpha times the area determined by x and y. What if alpha is negative? Technically, then the area determined by alpha x and y is the absolute value of alpha times the area determined by x and y. Notice here alpha x is oriented to the other side of y than x. It's more informative geometrically and more convenient algebraically to let A measure oriented or signed area, so that A alpha xy equals alpha axy equals ax alpha y for all alpha, including when alpha is negative. A change in sign of axy reflects a change in the orientation of the vectors x and y. Of course, we don't lose anything when we do this. Ordinary area just becomes the absolute value of axy. Viewers familiar with calculus may notice this is similar to how the integral of a real-valued function of a single real variable measures the signed area under the curve. The integral accumulates positive area when the function is positive and accumulates negative area when the function is negative. This provides similar algebraic benefits, including linearity of the integral. To get unsigned area, we integrate the absolute value of the function. Now, you might think that we haven't yet described much about the oriented area function, but remarkably, the two simple geometrically inspired properties we saw uniquely characterize the function up to a scalar constant. This means if f is another function with the same properties, then f is just alpha times a for a scalar alpha. The scalar alpha is the unit area assigned by f to the square determined by the standard basis vectors. To see this, first observe that these properties imply that ayx equals minus axy. Indeed, we have ayx equals ayx plus y by the addition property, which equals minus a minus y x plus y by the scalar multiplication property, which equals minus a x plus y by the addition property again, here adding x plus y to minus y to obtain x in the first slot, which equals minus a xy by the addition property again. In particular, it follows that axx equals minus axx, so axx must be 0. We describe this by saying that A is alternating. Notice that these properties are natural geometrically, Swapping x and y changes their relative orientation, so causes a change in sign of the oriented area function. And although a vector has one-dimensional length, certainly it determines no two-dimensional area by itself. The point is that these properties follow algebraically from the ones we already saw. Similar reasoning shows that for any three vectors x, y, and z, ax plus yz equals axz plus ayz, and axy plus z equals axy plus axz. It's worth pausing the video and proving these yourself. For example, for the second one, first show that if x is 0, then both sides of the equation are 0 using the scalar multiplication property. If x is non-zero, extend to a basis, express y and z in terms of this basis, and use the addition and scalar multiplication properties to derive the result. These properties, together with the scalar multiplication property, show that A is bilinear, which means it is linear in each argument when the other is held fixed. Now let E1 and E2 be the standard basis vectors. Express x and y in terms of them with scalar coordinates alpha1, alpha2, and beta1, beta2 respectively. Bilinearity of A implies that AXY expands like this. However, the alternating property of A implies that AE1E1 and AE2E2 are both 0, so the first and last terms vanish, while AE2E1 is just minus AE1E2, so this all reduces to this. Of course, AE1E2 is just 1, since A assigns the value 1 to the unit square. So this reduces to alpha1 beta 2 minus alpha 2 beta 1. Some viewers may already recognize this quantity, as it's just the familiar expression for a 2x2 determinant. This determinant is conventionally written in terms of coordinates alone, like this. Notice that we didn't need to compute lengths or angles of vectors in order to compute area. This is extremely important, and shows that area is an affine concept and not a metric concept. That is, it only depends on the vector space operations and not on an inner product. The oriented area function encodes much useful information. Under the standard orientation of the plane, AXY is positive if x is to the right of y. AXY is negative if x is to the left of y. And AXY is 0 if x and y are on the same line through the origin. This implies that AXY is 0 if and only if x and y are linearly dependent. So A determines with a single number whether two vectors are linearly dependent. This is one of the most important properties of A and why it's called a determinant function. We can generalize these ideas to higher dimensions and over arbitrary fields, not just the real numbers. In doing so, we're going to get a little more abstract and take higher dimensional analogs of the algebraic properties that we've already seen as the defining conditions for a determinant. Don't be alarmed by the abstraction. Keep in mind that these algebraic properties are motivated by the simple geometric properties we started with. Also, we'll come back to examine the 2- and 3-dimensional cases in detail later. To start, let V and W be vector spaces over an arbitrary field F. Let V to the k, or Vk, denote the Cartesian product of k copies of V. Here we're just thinking of this as k copies of the vector space V, not as a single vector space. That is, we're not adding or scalar multiplying k tuples of vectors from V. A map F from Vk to W is called multilinear, or k-linear, if it is linear in each argument when the others are held fixed. Here's what that looks like. For each I from 1 to k, f of vectors x1 through alpha xi plus beta yi through xk equals alpha times f of x1 through xi through xk plus beta times f of x1 through yi through xk. For k equal to 2, this is just the bilinearity property that we saw earlier with the area function. F is called alternating if f of vectors x1 through xk equals 0 whenever any of the two vectors xi and xj are equal. Again, for k equal to 2, we saw this property earlier with the area function. If f is multilinear and alternating, then a transposition of any two arguments causes a change in sign, as seen here where xi and xj have been swapped. As an example, if k equals 3, then f of x1, x2, x3 equals minus f of x1, x3, x2. In fact, since f is alternating, 0 is equal to f of x1, x2 plus x3, x2 plus x3. And since f is multilinear, that expands to this. However, since f is alternating, the first and last terms vanish, so we are left with this. Subtracting the second term from both sides of the equation yields the desired result. Essentially, the same proof works for any k. More generally, let sigma be any permutation of the numbers from 1 to k. Remember that formally a permutation is a bijection, or one-to-one correspondence, from this set to itself. But we just think of a permutation as a rearrangement of the numbers. Define the map sigma f from vk to w by the rule seen here. This rule says that to apply sigma f to any k vectors, first number them from 1 to k, then rearrange them according to the permutation sigma, then plug the rearranged vectors into f to get the result. If f is multilinear and alternating, then sigma f of x1 to xk is just minus 1 to the sigma times f of x1 to xk, where minus 1 to the sigma is the sign of sigma, plus 1 if sigma makes an even number of transpositions, and minus 1 if sigma makes an odd number of transpositions. Here we're using the familiar fact that every permutation can be obtained as a sequence of transpositions, and for a given permutation, the number of transpositions in any such sequence will always be even or always be odd. Therefore, this result follows immediately from what we saw on the previous slide. We now give these important maps a name. A map F from Vk to W is called a k-dimensional determinant map on V if it is multilinear and alternating. If W is the field F, then the map F is called a determinant function. Notice this definition doesn't make any reference to the dimensions of V or W. As an example, the oriented area function A that we saw earlier is a two-dimensional determinant function on the plane. Intuitively, a k-dimensional determinant map measures k-dimensional oriented volume. More specifically, it measures the k-dimensional oriented volume of the parallelepiped determined by any k vectors. However, we must be careful here. First, this geometrical intuition comes from working over the real numbers. Here we are working over an arbitrary field. Second, this intuition comes from working in low-dimensional spaces that we can visualize, like the plane. Third, a determinant map as we've defined it is in general vector-valued. It's not immediately clear how a vector quantity can measure a volume. Nevertheless, this intuition is still useful in guiding us to correct results even in the more general case, and the flexibility of our definition turns out to be extremely powerful, as we'll see. In a k-dimensional space, there is essentially only one k-dimensional determinant map. In an n-dimensional space where n is greater than k, there are more. For example, we've already seen that there is essentially only one area function in the plane. Any two such functions agree up to the unit area they assign. But there are truly different area functions in three-dimensional space, measuring area in different planes through the origin. We'll get more intuition for this a little later in the video. For now, let's make the uniqueness claim precise. Let V be an n-dimensional vector space over the field F. Let delta be a non-zero n-dimensional determinant function on V, assuming for the moment that one exists. Then we have a universal property. If F is any n-dimensional determinant map on V, then F is just delta times W for a unique vector W in W. In fact, W is just F of V1 to Vn for any vectors V1 to Vn with delta V1 to Vn equal to 1. This shows that delta is universal because every n-dimensional determinant map on V can be obtained from it in a unique way. In particular, every n-dimensional determinant function on V is just a scalar multiple of delta. To see why the universal property holds, we first observe that F is completely determined by its single value on a basis. That is, once we know the single value that F assigns to any basis, we know everything there is to know about F. Express arbitrary vectors xi in terms of the basis vectors vj using coordinates alpha ij as seen here. Plugging these vectors into F and expanding using multilinearity of F, we obtain this complicated-looking nested summation. Notice we've used the index variable j1 for x1, j2 for x2, and so on up through jn for xn. However, since f is alternating, f will be 0 whenever two of the j's are equal, so a lot of these terms vanish. We only need to sum over the terms where all of the j's take on distinct values from 1 to n. That is, where they form a permutation of 1 to n, like this. Here Sn denotes the set of permutations of 1 to n. Again, since f is alternating, we know how f behaves under permutations of its inputs, and this summation becomes this. We're left with a scalar, which is the big ugly summation in parentheses, times the single vector f of v1 to vn. Since the scalar only depends upon the inputs x1 to xn, this shows that f depends only on the single value f of v1 to vn. Note in particular, if f is 0 on a basis, then f is identically 0, that is, 0 on all inputs. By the way, that big ugly scalar is conventionally written in terms of coordinates alone, like this. This is the Leibniz expansion of an n by n determinant, and is often presented as a definition with no motivation or intuition. Aren't you glad that we're in the 21st century and you can see that this just falls out from the algebraic properties of a determinant function, which are themselves motivated by simple geometric properties? When n equals 2, this is just the expression we saw earlier for a 2 by 2 determinant. Back to the proof of the universal property. Since delta is non-zero, we can find a basis v1 to vn on which delta is 1. Indeed, by the reasoning we just saw applied to delta, we must be able to find a basis on which delta is non-zero, and then we can just scale one of the basis vectors so that the value is exactly 1. Let w be f of v1 to vn. Then f and delta times w are both n-dimensional determinant maps, which agree on the basis v1 to vn. So we must have f equal to delta times w. As a corollary of this proof, we also see that delta determines linear dependence. That is, delta of x1 to xn is 0 if and only if x1 to xn are linearly dependent. Indeed, if, say, x1 is a linear combination of the other vectors, then it follows from the multilinearity and alternating properties of delta that delta of x1 to xn is just a sum of zeros, which is 0. Conversely, if x1 to xn are linearly independent, they form a basis, so delta of x1 to xn must be non-zero since delta is non-zero. So delta is pretty cool, being universal and determining linear dependence and all. But how do we know that delta actually exists? We've only assumed that it exists, we haven't proven it. We can establish existence by induction on the dimension n. This is based on a fundamental relationship between n-dimensional volume and n plus 1-dimensional volume. Intuitively, an n plus 1-dimensional volume is just an n-dimensional base times a 1-dimensional height. But since we can't measure height directly in an arbitrary vector space, we proceed indirectly. First, the base cases. For n equal to 1, a 1-dimensional determinant function on V is given by any isomorphism from V to the field F. For n equal to 2, a 2-dimensional determinant function on V is given by any isomorphism from V to F2, defining A on F2 as above. What about n equal to 3? For this, we must analyze the relationship between 2 and 3-dimensional volume. We start from the top down, going from 3 dimensions to 2 dimensions, and then use what we learn to build from the bottom up, going from 2 dimensions up to 3 dimensions. To make things as geometric as possible, suppose that V is R3. Suppose further that there is a non-zero 3-dimensional determinant function. Fix any vector V and define A by AXY equals delta XYV. Then it is immediate that A is a 2-dimensional determinant function on R3. Indeed, it is obviously multilinear and alternating since delta is. This tells us intuitively that measuring volume relative to a fixed vector provides a way to measure area. Here's how it works. Fix any vector v. Now let x and y vary in any plane through the origin. To determine the area of the parallelogram determined by x and y in that plane, Just compute the volume of the parallelepiped determined by x, y, and v, and assign that number as the area. The function you get from this procedure satisfies all of the properties of an area function. Up to a scalar multiple, it's the only possible area function on that plane. Every two-dimensional determinant function on R3 is obtained from delta in this way. To see this, suppose that A is any two-dimensional determinant function on R3. We want to construct a three-dimensional determinant map on R3 using A, so that we can make a connection with delta. But how can we do that? Well, if we're given three vectors x, y, and z, one thing we can do is form the vector axy times z. Since A is bilinear, and scalar multiplication in a vector space is also bilinear, it follows that the map F which sends xyz to this vector is trilinear. So we're half of the way to a determinant map. Unfortunately, F is not in general alternating. If x is equal to y, then fxyz is equal to 0 since A is alternating, but if x is equal to z or y is equal to z, fxyz is not in general equal to 0. Luckily, we can solve this problem in a standard way using the alternator. Not that one. Given a multilinear map, the alternator produces an alternating multilinear map by summing over all signed permutations of the original map. In our case with F, the resulting map D looks like this. Don't worry about the scalar 1/2, that's just to make the math simpler later. The important point is that D is summing over all signed permutations of F. We obtain the expansion seen here. It's easy to see that D is multilinear since it's a sum of multilinear maps. It's also alternating. For example, if x and y are equal, then the last term vanishes, and the first two terms cancel each other out, as you should verify. The same is true if x is equal to z or y is equal to z. So D is a three-dimensional determinant map on R3. By the universal property of delta, D is just delta times v for a vector v. We suspect that v is our magic vector, and that axy is just delta xyv. Indeed, if x and y are linearly dependent, then both sides are 0. Otherwise, if x and y are linearly independent, then there is a vector z with delta xyz equal to 1, and we know from the universal property that v is just dxyz. Substituting this into delta, we obtain delta xyv is equal to delta xy dxyz. Expanding using the definition of D and multilinearity of delta, we obtain this. However, delta xyx and delta xyy are both 0 since delta is alternating, and delta xyz is equal to 1. So this just reduces to axy. This is exactly what we were trying to prove. Isn't that slick? If v is non-zero, which it will be if a is non-zero, we can extend to a basis of R3 and let pi be the coordinate functional for v with respect to this basis. Applying pi to both sides of the equation delta times v equals d yields this important relationship between delta and a. This relationship shows us how to work from the bottom up and define a three-dimensional determinant function in terms of a two-dimensional one. Indeed, if A is any two-dimensional determinant function on the two-dimensional subspace spanned by the two basis vectors other than v, and x bar denotes the projection of the vector x on this subspace, which is just x minus pi xv, then this equation defines a three-dimensional determinant function delta in terms of A. Delta will be non-zero if A is. This same idea can be used to define an n plus one dimensional determinant function in terms of an n-dimensional one for any n. Although it looks a little complicated algebraically, this definition ultimately rests on the simple geometric fact that n-dimensional volume is just n plus one dimensional volume measured relative to a fixed vector. In coordinates for n equal to 3, using the notation we introduced earlier, this relationship looks like this. This is the Laplace expansion of a 3x3 determinant along the first column. Again, this is often presented as a definition with zero motivation or intuition. Again, we're happy we're in the 21st century, and we can see that it falls out from the algebraic properties of determinant functions, which were themselves motivated by simple geometric properties. There's much more to say about determinants than I've said in this video, including applications to systems of equations, matrices, and linear transformations. My hope is that this video helped you better understand what determinants are and what their fundamental properties are. In future videos, I plan to cover applications of determinants. Here are the references I used in making this video. Page 1, page 2. Thanks for watching.